Hey folks, welcome to Clear My Paper. In today's episode, we are going to talk about two of the interesting topics, minor and cofactors. They're interesting by itself and they're also important because they define bigger concepts like adjoint and inverse, which we'll see in the future videos. So let's jump on to understanding what are minors and cofactors in the context of matrices and determinants. And if you recall from our last episode, we had talked about when we were I had put a bigger video of 30 minutes or so where I explained in detail how we compute the determinant of a 3 by 3 matrix. In that episode, there were key learnings which I've copied here and which we'll be discussing in detail in this while we kind of define what is a minor and what is a cofactor. And I'm not going to read it out, but we'll talk about the rows and columns of a matrix. We'll talk about the notion of submatrices, and then we'll talk about why the signs, algebraic signs, alternate when we define. And in the future video, we'll talk about the symmetry and we'll kind of try to unpack the symmetry which leads to the definition of Cramer's rule and adjoint and inverse of a matrix. So we'll cover the first three bullets in this video, okay? So let's get into that. So as always, I'm going to copy our good set of simultaneous equations which we have been taking as a baseline from the previous episodes on solving three equations and three unknowns in a generalized format, ABCD, which is what here it is. So the given equations, what we find here are nothing but we have y1, y2, y3 defined in terms of x1, x2, x3. So, and our objective was to find the values of x1, x2, x3. And in that context, what we ended up doing or deriving is we started computing the values of x1, x2, and x3 in terms of y1, y2, and y3. So if you see the right hand side after the equal sign has been reversed, and this is nothing but whether you can call it as finding a solution to these equations, set of linear equations, or even if you call it as finding the values of xy, x1, x2, x3, or you can also say we are inverting the equation instead of finding, we are taking the given equations in terms of y and we are trying to express in terms of x. So all of that mean the same over here. And while doing that, while getting the values of x1, x2, and x3, what we have done is we have taken the determinant, and like we discussed, determinant can be taken across any row and any column. While doing this piece from the last episode, I have written the equation again for quick reference. So what we have done is we have taken the first column. If we take the first column, because what we are going to do is we want to get rid of x2 and we want to get rid of x3, which is this column and this column. And that means we just need to keep x1. So what we have done is we have just considered this column over here and we have taken the determinant on this column for each of these elements for x1. And similarly for x2, we have taken this column and we have knocked off the remaining columns, and for x3 we have taken this is x1. So that's what we have done for each one of them. So for x1 we are taking the first column which is related to x1, and for x2 the second, and x3 the third. Okay, and we have got we have found the values of the x1 in terms of ratio of two determinants, or we can focus on numerator and denominator. And what we found is the denominator, which is the determinant of this coefficient matrix over here in terms of coefficient, that remains the same regardless of however you compute it. If you see the denominator while finding x1, the variables and the way they are multiplied are different than what we did for x2, than what we did for x3. So the sequence of variables, what's being multiplied and what's being added are different, but the answer is going to be still the same, because the determinant does not change and the denominator cannot be 0, or the determinant cannot be 0 for the solution to exist. We have kind of learned that for the denominator part, and that's the reason regardless of which row you take, while if you want to find a determinant of a 3 by 3 matrix, which row you take, in this case we took the first row for each of the element, or we took the first column. So it does not really matter which row you take or which column you take, the determinant does not change. And that's what the first learning is. Any row, any column. The determinant of a 3 by 3 can be used or can be found using any row, any column. The answer does not change. So this was the first kind of a statement that we are trying to re-emphasize. And next we'll move on to the concept of submatrices, which we discussed earlier also. So let's focus on this one. So let's take let's take this space over here. Okay, so let's say we have a given matrix like this, and we are going to find the determinant. And in this case, if you see, as opposed to the previous cases where we are going column by column, in this case, the example is this image I copied. All these images I copied from the Google Internet, so it's not my own. Just a disclaimer. In this case, they are taking the first row. They are taking this row, and they're trying to determine or derive the determinant of one element at a time. So first they have taken A, and then you see they're forming a submatrix or a minor matrix here, a small matrix here. Then they're taking B, and they are forming this purple here, this matrix here, and then C and this matrix here. So they're taking one element of the first row. So in this case, the consideration is the first row. They're taking the first row, and for each of the element, if you see here in this format, the effect is as if they're multiplying a scalar by a smaller submatrix, and the smaller submatrix nothing but, as we discussed, the very element that you're considering. If you exclude the row and the column, that element is present. If, for example, if I'm finding the submatrix for element A, if I exclude this row and exclude this column, whatever is remaining, that's what this determinant is for. So like that, when I try to express the determinants, in this case it was the first row. Or if I take a different example where we follow this nomenclature where each element has a row number and column number attached to that for each of reference. This is row 1, row 2 and row 3, and this column 1, column 2 and column 3. These are columns C1, C2, C3, and these are row 1, row 2 and row 3, and the first number is the row and the second number is a column. For example, this element is on the third row. This is a row 3 and column 1. So if I follow this nomenclature, applying the same concept as we did on the left side, but in this case, this is applying on first row. We're taking the first row into consideration over here, but over here they're taking the first column into consideration. If you see all the one in the green color, A1, 1, A2, 1 and A3, 1, this is what they're taking into consideration for finding the determinant. And all the things that you see in the brown are nothing but the submatrix or the matrix of 2 by 2 that we discussed here. Whatever is in the purple color, that's the one. If you see A1, 1, this everything in the brown color is a submatrix. So this submatrix is nothing but a minor of the matrix. That's what it is called. We already saw in the last video, but I wanted to officially put this video for the definition. Just the submatrix. Don't worry about this coefficient here or this coefficient here, and don't worry about the alternating plus or minus, and we'll come to that. Just the submatrix part of that, this part between the two vertical lines, this part between the two vertical lines, or all the elements in the brown color over here, this part. This is a determinant, right? When you cross multiply the diagonals, just the cross multiplication of the elements within the submatrix is called as a minor of the element which was excluded to start with. So the minor of A11 is this element, this value in brown color, A22 minus A22 into A33 minus A32 into A23. Likewise, the minor of this element C, when you consider the first row, whatever is the determinant of this, DH into EG, whatever is this value is, DH minus EG, the value of that is nothing but the minor of this element which was not considered when we found this determinant. So that's the definition of minor. It's nothing but the submatrix or the minor matrix that is formed. And again, if you see here, in this case we are taking the first row, in this case we are taking the first column. It does not matter how you calculate the determinant of a matrix, the answer is going to be the same. So that covers the first 2 points over here, any row, any column, and the notion of submatrix. So the notion of submatrix is a smaller matrix, and that leads to the definition of minor. That's what we discussed in the last video, and in this episode we are kind of officially defining what is a minor. Now let's move on to the last part, which is the cofactor. So if you see here, this matrix, it looks a lot of numbers, but it's a very simple thing. What we have done is, for each of the element in the given matrix, whether you take on the format with the row column number entered, or you can take a simple co-matrix that is in this case. So if I have to compute the minor of each of this element, which is a 2 by 2 determinant, and put in the format, this is how I will get it. So for example, the minor of A is nothing but I need to exclude the row in which A appears, and exclude the column in which A appears, and whatever remaining thing I take, the determinant of that is the minor of this element A. I'm entering it here. So this matrix over here is nothing but matrix of minor of each element in A. That's what it is, right? Each element in A, in the matrix A. So this determinant are nothing but the minor of each of this element in this given matrix that we already know. So I'm just expressing this in this format. I'm just trying to bring all these things together. Instead of just putting one row at a time, I'm expressing the minor. So what we have is in this left side, we have got 9 elements, A from element A to element I. So the total there are 9 elements, and that means for each element I need to have a minor. And if you see here, there are 9 minors here. So we have got 9 minors here, and we are forming a matrix of that. So this is a matrix of the minor of each of the element. That is. And what is a cofactor? In the last video, we did see that, right? For example, if you see here algebraically, over here, x1, x2, you can take any of the equation and you can focus on the denominator or you can focus on the numerator, does not matter. What we end up doing is each element or each of this determinant, this is the kind of the minor, right? All of these are minus in the determinant. And if you see the algebraic sign alternates between positive and negative. So over here we have negative and this is implied positive, and over here we have positive. Similarly, if you see here also, it starts with a negative, and the intuition behind why this alternating comes from here, because when we try to eliminate x1, x2, x3 based on what we are finding and we are trying to multiply them, naturally we come into this equation, which is what we derived in the previous episode. But every time you see the denominator or even the numerator, but we're focusing on the denominator in this case, the algebraic signs are alternating. So we have minus, if it starts with minus, then we have plus, we have again minus. And similarly for x3, it starts with plus and then we have minus here and then we have again plus here. So the signs are alternating, and the reason is the way the algebraic computation works. That's the reason it's alternating. But if we kind of put that intuition in a matrix format where we are trying to bring the flavor of alternating signs, so what happens is we have the minor of the matrix and the signs should be alternating based on the coefficient. So we'll start with the first element will be always plus, and then each sign is alternating. Then we have negative, then we have plus. Even if you go column wise, we have positive, we have negative, then we have positive. Again, if you see here, it's alternating. So the effect that it kind of gives is easy to remember. Like what happens is anything that is on the diagonal, both the diagonals is positive. Any data elements on both the diagonals are positive. So we have 9 elements and there are going to be 6 elements, 1, 2, 3, 4, 5, 5 elements on the diagonal. So 5 of 9 are going to be positive. So both the diagonals are positive and the remaining things are negative. So this is an easy way to remember how to kind of get back into the algebraic signs for the minors. And this very fact that the signs are alternating for each of the minor, if you take the minor along with this alternating sign, then we get to the definition of something called as cofactor, which is what is defined here and here, cofactor. That's what the definition of cofactor is. The cofactor of a matrix is nothing but you take the minor of each of the element of the matrix and then you follow this rule of positive and negative sign alternating between each other. The row 1 and the column 1, the first element will be always positive and then you can alternate. You can either remember that way or you can think that, okay, all the elements on both the diagonals are going to be positive and remaining is going to be negative. You can think from that standpoint as well. And what that would mean, and like I said, it comes from the basic denominator, how it's algebraically derived. So if in case you need to understand where it came from, you can understand from this part. That's how we are forming the notation. In case you really don't care, you just want to understand a shortcut, how to remember this formula, and this is what it is. So what we have derived so far is a cofactor of a matrix is nothing but you get the minor of each of the element in this format and then start alternating the sign. So the combination of the minor and the algebraic sign is nothing but a definition leading to what is a cofactor of a matrix. And the same way, if you are going to follow this kind of a matrix where you're going to number each of the element in terms of row and column, the same thing it means. So each of the thing in the determinant over here is nothing but a minor of an element which is excluded. For example, this is the minor of A11, this piece is a minor of A12, and so on and so forth. And then when we start alternating the signs starting with plus, then we get something that is called as the definition of cofactor. So that's what it is. So I just wanted to give you a perspective of what it means in kind of, again, we're summarizing here. So minor of an element, what is the minor of an element? Is determinant of the submatrix or the minor matrix, excluding the row and the column of the very element for which we are finding a minor, which is what we discussed. For example, if you're taking this example, if you're going to find the minor of A11, then we exclude the row and the column where A11 is. For example, I'm going to exclude this and exclude this. Whatever is left over, that's the minor of this A11. And what is a cofactor? Cofactor is nothing but you prefix a plus or minus sign alternating based on the above rule to each of the minor, and whatever matrix you get with a signed minor matrix, that's nothing but the cofactor. And why these are important, you will get, because when we condense it, this definition by itself does not have any meaning. But when we try to solve equations, and if you want to really memorize how to solve this equation, for example, in the examination, if you get, hey, solve this equation using some Cramer's rule or using a determinant, there is no way you can remember this formula and the sequence of variables and all those things, because it's not consistent. There are many ways to do that. And there has to be a compact way to remember how to do that. And getting the notion of defining a minor and cofactor will help you in remembering the formula, meaning that when this matrix is given, instead of solving it this way, what you're going to do is you're going to take any matrix, and you know that if you have to find the value of x1, x2, x3, what we need to do is, or even if you want to find the value of a determinant, you know that you need to put this in the matrix format, this format, and then you can start expressing that in the terms of minor, and you can start adding and subtracting that. Further, you need to bring in the cofactor, which is alternating sign, and the whole effect of that will give you the denominator, the determinant of the matrix, which is what it is, right? It's a minor multiplied by the coefficient, and there's alternating signs. So to remember that, how to do that, we kind of express them into this format, which will be easier to memorize and which you can apply for real-time problem solving. That's the whole effect of that and impact of that. So that's a wrap up on this episode, guys, on minor and cofactors. Hopefully you enjoyed this and you just got an intuition on where the very textbook definition of minor and cofactors are coming and what is the algebra behind that. Hope that was useful. And in the next episode, we will kind of continue. It will be a natural segue to talk about two more important topics, which is more like culminating the end of matrix and determinants as a whole syllabus, that is adjoint and inverse. So stay tuned. Signing off on this episode from Clear My Paper. I'll see you in the next video.